All right. I don't know if we'll get to that partially full pipe example. I've got that in the notes as the last lecture. If we do, then you'll need the computers. If we don't, then you won't. You won't need the computers up front anyway. So your final assignment of the semester is due on Friday, as we talked about before. If you have any questions about that, I'll be in my office today during my office hours, and then I probably will be in during the morning tomorrow as well, before I leave for going down to Clemson. So you're welcome to stop by tomorrow morning if you've got any questions. For our final exam, I brought the sign-up sheet just to review who wanted to change final days, and so I've got Jonathan Lambert switching to Friday, Tyler switching to Friday. Were there any others who wanted to switch to the Friday exam? All right. Yep. Okay. Any questions about the announcements? The perfect storm. I think I heard somebody recognizing what that was at the beginning of class. The perfect storm occurred back in the early 90s when 3 storms hit the same spot at the same time. The leftover remnants of a hurricane that had sort of petered out. It never really made landfall in the United States. It was a hurricane that sort of swept through the Caribbean and had lost most of its energy, but it was still a storm nonetheless, and a nor'easter, which is a storm coming from the northern part of Canada headed towards the east, and then a storm that had already been in the Atlantic Ocean for a while. These 3 storms came together all at once, and there's the movie that stars George Clooney and Mark Wahlberg, right? Yeah, as fishermen out in the North Atlantic. And
I remember that storm. It actually flooded some parts of the town I
really?
grew up in. Yeah.
Where was that?
In New Jersey, Tuckerton.
And what year was it? Do you recall?
1990.
90? Yeah.
Yeah, I was pretty little at the time, but
yeah.
I do remember it.
It was a big storm, and they say that it was a perfect storm because it doesn't come around very often. And well, the first couple of problems in your homework assignment for Friday are related to probability and risk. And so I just wanted to point out the relationship between probability and risk. In any given year, there's a probability that a certain size storm would come around. This 100-year storm that they had out in the Atlantic Ocean, in any one given year, a 100-year storm has a 1% probability of occurring. And so probability and return period are reciprocals of one another. The annual exceedance probability at 1% is the reciprocal of the 100-year storm. Now, the relationship between risk, I wonder if I didn't bring my notes today. I'm going to have to go grab those. The relationship between risk and probability is shown on the screen here. And so if we have a 200-year storm, then the probability of a 200-year storm, 1 over 200 is the probability of a 200-year storm. And if we want to know what's the risk that one of those storms will come through during a window of time that's a 50-year period, maybe a 50-year period being the design life. So N would be 50. And so what's the risk that we'll have a 200-year storm come through in a 50-year period? You might just think, well, it's a 25% risk. But actually, it's not quite that simple. So 1 minus the probability, 1 divided by 200, and that is to the 50 power. So I didn't bring my notes. I'll do the calculations along with you, and we will find the risk.
like these storms changing on a daily basis, or, I mean,
Like what's considered a 100-year storm? Is that what you mean? No, they're not changing on a daily basis. They have to have about 100 years of precipitation data to know what a 100-year storm looks like. And so any one day out of a period that long isn't going to really change the balance of what's considered a 100-year storm.
you had two of them in like a 10-year period.
It's possible.
It is possible.
Yeah, sure. It's not impossible to have two big storm events in the same year that are greater than the probability might indicate would happen, but it's just a matter of risks rather than certainty. So there's only a 22.2% chance. Does everybody get that same value? 22.2% chance that during a 50-year period you'd see a 200-year storm. So,
If you're designing like a channel or something and it's been like 70 years since the last 200-year storm, do you compensate?
you don't, yeah. In some, and I can understand where your question's coming from because, like, for example, in earthquake risks, they do think about how long it's been since the last big earthquake. And with an earthquake, actually, how long it's been since the last earthquake, the energy builds up in the plates, and so the amount of time it's been since the last one does have an influence on how big the next one will be. But that's not true in the case of precipitation events. How long it's been since the last big precipitation event doesn't have an impact on the probability or the intensity of the next one that may occur. That's a good question.
Is that 22.2% that one will occur or one will occur where you're at?
What's that?
The 22.2%, is that just 100 or 200-year storm will occur in general or where you're located?
Oh, it's in the location that you're at. Yeah. Yeah, so there's one, there will be a 200-year storm every year somewhere. It's just in any given spot, during the 50-year period. All right, so we're talking about channel design today, and this is showing a man-made channel, trapezoidal. It's an irrigation canal that's going through a residential area. One thing to point out from this image is that there is a fence near it just to keep kids out. Another thing is that oftentimes on either side of an irrigation canal there will be right-of-way so that people who are inspecting or maintaining the canal can drive alongside in a pickup truck and pick up trash that may accumulate in the canal. This is a channel that isn't quite as sophisticated as the concrete line channel, but here it's just sort of a grass-lined ditch that's meant to convey flow from, I think it looks like an orchard. A open channel may be lined with riprap or broken up rocks or concrete. This is showing water coming from a culvert, and it goes around a bend here, and they've installed the riprap just to ensure that it's not scouring the earth and trying to make it a little bit more durable as water flows out and joins the main channel here. And here's construction of what will eventually be an earth-lined channel. When they have a channel that's made out of earth, they have to compact the clay. They have to make sure that the side slopes are going to be stable, and so they wouldn't ever really achieve a slope that steep with an earth-lined channel. What material to use and how wide the channel should be depends on factors beyond just what we'd expect, the flow capacity Q that we'd solve using Manning's equation. There are some other considerations that factor into it, such as the velocity of the water. And last time in class when we were speaking about sewers, we talked about how the deposition of sediment in a sanitary sewer can reduce the capacity of the sewer. And so velocity is a concern in sewers, and it's also a concern in channels like this because we want to have enough velocity to scour sediment, to keep sediment suspended, but not so much that it maybe would be damaging to the grass lining of a channel. And so what type of lining to have, whether to put concrete onto it, partly depends on the velocities that are going to be anticipated. And in some cases it's good. Here maybe we would want to have as much infiltration as possible. If it's stormwater that's considered an undesirable waste, sort of a waste product, stormwater runoff, usually you want to get rid of it. It's a nuisance, so you try and encourage infiltration. But if it's irrigation water that you're trying to get to an area that's being farmed, then you would want to avoid infiltration, and so a non-permeable liner like concrete or sometimes a plastic liner will be put down in the canal to try and avoid infiltration. So there are a variety of considerations that have to be accounted for when picking the cross-sectional shape and the liner that's used. This picture is an irrigation canal in Florida, and Florida sort of has a lot of these very long, very straight, unnatural irrigation canals that were put into place to drain swamps and try and increase the amount of land that can be farmed or built onto. The best hydraulic section is the one that can accommodate the highest flow for a certain cross-sectional area. And we've looked at these best sections before, the shapes that, for example, the half square for the best rectangular section, and the side slope that goes along with the best trapezoidal section, the one that is going to have the maximum flow rate per flow area, the biggest Q for a certain cross-sectional area being excavated. And so we can solve for what flow area is needed for a certain flow rate and slope and wetted perimeter, rearranging Manning's equation that's shown there. So just from a hydraulic standpoint, our first thing that we want to do is reduce the amount of fill that has to be removed, reduce the amount of excavation. So minimizing the cross-sectional area is going to reduce how much soil has to be excavated to put in a channel. And what you have direct control over as a hydraulic engineer is really only just the Manning's end by choosing what material the channel is going to be made out of. The slope oftentimes isn't in our control. You can't increase the slope anyway. Sometimes you can decrease the slope of a channel by causing it to meander back and forth. And I think I've illustrated for you before that if you have water going down a hill, if it's going in a straight line, there's some delta Z. If water is flowing from 1 to 2, then the slope is going to be delta Z divided by L. And so if you have a straight channel, you have a relatively short L. But a channel that meanders back and forth still has the same delta Z to get from point 1 to point 2, has the same delta Z, but by meandering, you've increased the length of it. And so its effective slope is lower. So sometimes hydraulic designers, if the velocities are too high and they're worried about scour, may choose to meander a canal.
So I know we know how to determine Q and all that stuff, but when you're designing a channel, what are you designing for? What Q? Is it like a 100-year storm? Is it a 10-year storm?
Well, that brings up a good point between the division of a hydraulic engineer and a hydrologist. The hydraulic engineer is given Q, design the channel. Well, the hydrologist or the hydrologic engineer is the one who gives you that information. So as a hydraulic designer, you can just assume that you'd be given some flow rate to design for. Well, as it turns out, you might also be the person who's doing the hydrologic design. But there are two distinct phases: determining the Q that's going to go into the hydraulic design, and what goes into the Q that's determined. It may be rainfall, it can be the basin properties, and return period. So in a freeway, like the interstate, they specify that the return period storm that should be used for an interstate is a 100-year storm. And when they put catch basins along the side of a freeway, they don't want any puddling or pooling to occur on a freeway during any storm smaller than a 100-year storm. on a road like we've got here in Huntington, just 3rd Avenue, I don't know what it was originally designed for, but it fails certainly far more frequently than a 100-year storm. It probably a 1-year storm is enough to build the lanes. And by failure, the criteria that's usually used for failure is if you have a road, and here's a curb. If this was a 2-lane road, so this is the number 1 lane, this is the number 2 lane. If more than half the lane has water in it, that's considered failure. So by that criteria, 3rd Avenue fails quite a lot. So, but back to your original question of what flow rate would you use? You'd use the flow rate that you're given from the hydrologist, and maybe it would be a collaborative thing because the hydraulic designer would have to know what the design standards are for the type of road that's being built, or for a dam, maybe a 500-year return period that has to be designed for. So it varies. It depends.
So it's specified on the job.
Mm-hmm. Yeah. Or sometimes you just have to use your engineering judgment. There may not be a code that applies, but the question that you ask yourself is, how often do I want this to fail? In the case of a channel that's going through a neighborhood, people would be pretty irritated if the water levels got so high that it flows into their yard. And so you'd maybe have a pretty small appetite for failure. But if it's in a rural area and this channel fails, maybe it's just that the nearby orchard has a couple of inches of water in it for a couple of days, you could probably tolerate that failure. And so there's no sense in putting a lot of effort into a great conveyance channel in a rural area where you don't mind failure. All right. So remember, our best trapezoidal channel was the one that has side slopes, √3 divided by 3. That's talking about how steep the side slope is. And that's steeper than a 1-to-1 side slope. And so it's pretty steep to get this best trapezoidal channel that will have the most conveyance for its given area.
Concrete only now.
Yeah, or rock, if it's excavated out of rock. Pretty unusual to do that. Freeboard is the excess depth that you want to apply in order, you can notice that the water level gets to a certain point. You wouldn't necessarily design for the water level to go up to the very top of the channel. And so freeboard is provided in case there are wind-driven waves. You can imagine that on a windy day there might be some splashing of the water, and so you wouldn't want the water all the way to the top if there's ever a chance of those wind-driven waves. It may be just some excess capacity for safety factor. It may also be for something that's called superelevation. And if this channel is going straight, then the water level will be straight. But if a channel, now in a top view, if a channel is curving, think about what happens in a car when you're going around a bend. Everything sort of shifts to the left of the car. And so the water in a channel will actually have a little bit of a slope to it if you're going around a bend. Now this is exaggerating, but superelevation due to curvature around a bend, especially for high velocities, can add a couple of inches depending on the width of the channel. So freeboard is that extra height that you provide for any of those things. So the side slope, how steep the side slope is, depends on what the channel is made out of. And the overall costs that have to be considered may be the cost of disposing of the excavated material, trying to avoid the expense of real estate and right-of-way. It may be more economical to have the channel be relatively deep and narrow to try and avoid having to purchase a really wide right-of-way. Excavation, in other words, may be cheaper than the real estate costs, and so you'd make a deeper channel rather than a wider channel. So there's just a balance of considerations that have to be taken into account. This is, again, another summary of those best, most efficient channel sections that we've seen previously. And remember that there are two different slopes that we have to consider. The longitudinal slope is the slope that goes into Manning's equation. That's the slope of the channel itself. And if a channel is too too shallow, then we may not have the minimum velocity that we're looking for. And in some cases, in addition just to keeping sediment moving along, a minimum velocity may be desirable to help weeds avoid growing. If you have a velocity that's really slow moving, then weeds can grow in the channel and can eventually choke the channel. But if there's always enough velocity to keep the weeds tipped over, then it can sort of inhibit their growth, and that avoids the expense of sometimes channels have to be mowed. They'll have they look like dredging boats go, and they'll actually mow a channel to keep the vegetation down. So slopes can have an effect on the maintenance issues that will crop up longer down the line. And the side slopes are going to be governed by the material that's selected. And this is showing what types of side slopes can be achieved for different material types. You need rock maybe or concrete to do a vertical rectangular channel. And it would be feasible with a really cohesive soil like peat to have 4 horizontal for every 1 vertical. And that's just so that it's not falling apart. If you have fast-moving flow, then there could be erosion even of a peat soil. But for sand, 2 to 1, sand, loam, porous clay, 3 to 1. And these are bare minimums. For it to be a little bit more safe, they'd have even more gradual side slopes than these. All right, so freeboard, we talked about that extra capacity that's provided for wind-driven waves and safety factor or super elevation around the bends. And there's an empirical equation that's used to just give a suggested guideline of how high the freeboard should be. This is in in SI units, this empirical equation. So there's a linear interpolation of this factor C, and you can, if you know the depth y and the flow rate that's going to be expected, use this empirical equation to estimate how much freeboard is required. And this equation for superelevation height tells you how much vertical elevation difference there's going to be between the right-hand side and the left-hand side of a channel based on the top width of the channel and the velocity that the water is traveling. This takes angular velocity into account and the radius of curvature, and tells you how much of the water is going to be sloshing over to the left-hand side if you were banking to the right. A lined channel is more expensive, but comes with some advantages that for a steeper slope where velocities are going to be high, it can allow the steeper slope. And if you have a steeper slope, then of course that also reduces the cross-sectional area that's required for the same flow rate Q. And if water is expensive and you're trying to preserve it for irrigation or other beneficial uses, then a lined channel will decrease the amount of infiltrated water. To design a lined channel, you first have to select the material and the N value that goes along with that material. We estimate the roughness and the freeboard coefficient, C. The freeboard coefficient, of course, was selected partly based on the flow rate. Calculate the normal depth of flow with Manning's equation. Checking the velocity and the Froude number will let you know if there's likely to be concerns with scour. And the guidelines is that the velocity shouldn't exceed 2.1 meters per second if it's non-reinforced lining, meaning a packed clay. And if it is reinforced concrete, then it's okay to have supercritical flow or a velocity up to 5.5 meters per second. And if you're going to go beyond 5.5 meters per second, then time to call in the big guns, because it's really going to be pretty dangerous, and it would have to be probably a specialty concrete in order to avoid scour. So let's go through this design process here where we're going to design a trapezoidal channel. The question is, how big should the channel be to carry 2.4 cubic meters per second, where we know the longitudinal slope is 0.5%. All right, while you are conservative, sometimes you'll assume higher than that. Kind of a midpoint value for concrete would be 0.015. So yeah, let's use concrete for this one. Concrete and midpoint min value 0.015. Okay, the freeboard that we're going to need here, if we interpolate the C value, C is 1.5 at 0.57 cubic meters per second and 2.5 at 85 cubic meters per second. So essentially, we're going to be linearly interpolating between 0.57 and 85. It goes from 1.5 to 2.5. We're going to be somewhere in the middle there, 2.4 cubic meters per second. The slope of this is 0.01184 per cubic meters per second. There's no units on the C value, so that's why it's no units per cubic meter per second. So the C is going to be 1.5, which is the C value that comes along with 0.57, plus the slope times the additional flow that we have beyond that base. Okay, our total flow is 2.4 cubic meters per second. So 1.83 is 2.4 minus the 0.57. So the C value overall that we'll use, 1.522. Just linear interpolation there. For the normal depth of flow, let's assume we're going to use the best hydraulic section. That means that our wetted perimeter will be 2 times the square root of 3 times the depth. The area will be the square root of 3 times y squared. B is 2 root 3 divided by 3 times y. And M is root 3 over 3. Okay.
You have to add the base to the word perimeter.
I don't think so. This is for the best hydraulic section. And so, let's see here. Where did I have those? Yeah, so a trapezoid. The wetted perimeter is just a function of the depth. Yeah. All right. So Manning's equation, Q is A divided by N, area divided by wetted perimeter to the 2/3 power, slope to the 1/2 power, 2.4 cubic meters per second, root 3 times y squared as the area, our 0.015 for the N value. The area will be root 3 times y squared. Wetted perimeter is 2 root 3 times y. That is to the 2/3 power. And the slope, 1/2 power. Okay. From that, we can get that the depth is 0.7514 meters. And then, based on the other parameters for wetted perimeter, top width, and everything else, that leads to that the channel bottom width will be 0.8676 meters. The side slope of the channel is 0.577, and the top width is 1.7357 meters. Okay. What will be the flow velocity in this case? We just get it from Q divided by A. So we had 2.4 cubic meters per second. And the area is the square root of 3 times y squared, 0.7514 meters squared. Okay, so the velocity is 2.45 meters per second. So that's good. In that range, it's going to prevent sedimentation. If we go above 0.9 meters per second, then that will keep soil particles suspended in the water. And it also is good because it will prevent vegetative growth. It's going to ensure that it keeps weeds pushed over, and that will slow down and inhibit their growth. So that's okay. Freeboard, how much extra depth to provide beyond the actual flow depth. The freeboard that we should count on would be 0.55 using this empirical equation. Our freeboard coefficient was 1.522 times the depth is 0.7514 meters. Okay, so the extra that we would provide is 5.588 meters. So that means that our channel that we construct is going to have a bottom width of 0.8676 meters. The flow depth is going to be 0.7514 meters. And then the extra distance above the water surface up to the edge of that trapezoidal channel would be 0.588 meters. So that's just a very quick look at how to design a lined channel.
Do we need to check the ground?
Yeah, we probably should. Let's see.
What do you think the minimum velocity should be to prevent vegetative growth?
It depends on what sort of vegetation there's likely to be there, and then also sometimes it depends on what's in the water. Nutrients like nitrogen and phosphorus can really stimulate vegetative growth, and so, if it's a mountain stream, it probably could be slow moving and still wouldn't support very much vegetative growth. But if it's coming out of like a farm area where they add a lot of fertilizer to the soil, then maybe even fast-moving water would promote vegetation.
Is it actually necessary to check it?
Well, since we're using reinforced lining, probably not. Yeah. We've got concrete. Okay, just one last thing I wanted to point out, and I think you do have a homework question related to this, is an unlined channel. So if it's an unlined channel, the cohesive strength of the soil is something that you're going to try to not exceed. If you have shear stress that's too high, then it will shear the water, it'll shear the soil, the sand, whatever material has been used for lining the channel downstream. And so you're trying to have velocities high enough that there isn't sedimentation of whatever particles are suspended in the water, but low enough that it preserves the integrity of the channel itself. And so the design process is similar, where you would do a geotechnical analysis and find out what's the maximum allowable shear stress that can be tolerated. And then from that maximum allowable shear stress, there's a relationship between, let's see, do I have it on here? No. Oh yeah. There's a relationship between the shear stress and the slope of the energy grade line. So, for example, in a homework assignment, if they told you the allowable shear stress in the soil, that would mean that you have a known for the shear stress of the soil, then you could calculate the slope of the energy grade line, S of F, and then put that into Manning's equation and find out what sort of cross-sectional area is required for a certain flow rate. And in fact, I think that's the process that you'll need to follow in the homework assignment that goes along with an unlined channel, is with a given shear stress, solve for the slope, and then once you have the slope found here, put it into Manning's equation. Well, unfortunately, that's all the time we have for today. The slides that we didn't get to, we're talking more just about these guidelines of what sort of velocities can be supported on a grass-lined channel, and different types of linings that are sort of in between bare earth and concrete lining. You know, the grass helps to keep the soil together, but obviously isn't going to be as strong as concrete. So that's it for today. Remember that the lecture that we have